I think we should start. Welcome, everyone. Thank you for taking the time out of this beautiful day, beautiful fall day, to attend this mini workshop on data science and natural language processing to find rare entity classes from text. Next, we so just to kind of get a because I think there will be a lot of graduate students here, I wanted to start with a little bit of a pitch. You all might know already of the MIDAS certificate, but I also wanted to kind of highlight a precision health graduate certificate program that is run out of the precision medicine, the precision health initiative. And for the certificate program, the Department of Learning Health Sciences is the home. And for those graduate students who are current graduate students of University of Michigan and who are interested in understanding healthcare in a multidisciplinary data-driven based approach, this might be a certificate you might be interested in. If you need more information, please contact phcertificate@umich.edu. Next. So let me kind of start with introducing the two speakers. I am Vinod Vydiswaran. I am an assistant professor in the Department of Learning Health Sciences in the medical school. And I also have an appointment as assistant professor of information in the School of Information at University of Michigan. I'm joined today as a co-presenter by Xinyin Zhao. Xinyin is a PhD candidate in School of Information and has been a critical member of my research group for a few years now. Next. Just some administrative items to start with. All participants are going to be muted for the duration of the webinar. And if you are unable to ask questions or something through the question and answering forum, Trisha, he is here from MIDAS to kind of offer technical assistance to make sure that any questions that you would want to ask can be raised through the webinar interface. We will we will monitor the Q&A window through the webinar, but we would take questions probably at specific times during the talk so that the transition is more smooth. But please keep your questions coming. We just realized that some of the questions would come in as anonymous. So if you are willing to share who's asking the question, also that would be really appreciated so that we can direct it personally to you and follow up with you after the end of the webinar if possible. The talk is in a way structured. Yes, next, thank you. It is structured in 3 parts. Just so you know, it is a 1.5 hour talk, but we plan to present in basically the first 50 minutes to 1 hour, and then have ample time for questions and discussion at the end of the webinar. The talk has 3 main parts. First, we are going to kind of introduce rare entity classes, and that is a subjective definition. So we want to kind of highlight that a little bit more, and then use that to look at how data science and natural language processing approaches could be used to identify rare attributes and rare entities from free text. Most of the examples would come from medical domain, but there are examples spread across open domain natural language processing. So we will talk about really examples coming from social media, legal domain, and so on as well. Next slide. So let's start with the challenge of big data. And in this particular case, I'm taking an example from health as the motivating example. Health data is generated from a variety of users. The professional view, or those that are generated by health professionals, come in terms of diseases, diagnoses, procedures, lab reports, and really the professional lingo of medicine. And on the other hand, we have these coming from books or from medical records, paper records as shown in this illustration, but more and more in electronic form. And then next, also coming from information that goes into the pill bottles from a pharmacy, right? Where again, the instructions that are given by the health professional, by the prescriber, get transformed at a pharmacy into into language that is easily understandable by patients and by those who are going to take the medications. Next. On the other hand, there is a consumer view of data, and that consumer view is what patients, uh, their loved ones, their caregivers, family caregivers have access to. So typically, when we as lay people try to search for health information, we would go on Google and type in a query. And we would get pages such as these from WebMD, or next slide, from health forums. So in this particular case, this one is from a cancer forum where uh, patients and their caregivers have sent out information about what kind of cancer they have and what stage of cancer they are in, and kind of seeking assistance in terms of finding others who might have some similar conditions. Next. Information could come from sources curated by the community, such as Wikipedia, where this information is not necessarily written out by a health professional, but is accessed extensively widely. And then next, using tweets, where these tweets do come from experts, because in this particular case coming from CDC, but they are in a format that is easily consumable by lay people, right? So in this particular case, these are talking about whether someone with Ebola can spread it to others. And I could very easily find examples using COVID and so on. I didn't want to take a topic that is closer to where we are right now. Next. So let's take an example of this free text data that in healthcare, and take an example of the WebMD image that we have seen before, to look at what actually it is being shared on that page. The title is Erbitux Helps Treat Advanced Lung Cancer. So we know that this document is about Erbitux, which by context we know is a drug, a medication, and it is used to treat advanced lung cancer, which again from context we can infer is a disease. Let's take another example next. And here, this is from a few years later, and talks about cetuximab benefits patients with advanced lung cancer. I'll leave this slide a little bit for you to see and come to a conclusion whether they are really giving the same information. It doesn't say Erbitux, but it says cetuximab in the second one. But if you read the first line, it kind of says that cetuximab actually is Erbitux. The brand name for this agent is Erbitux. So indeed, it does give you the same information. And but they are two independent sources, if you want to kind of say it that way, because one is 6 years later, probably following another study on the benefits of Erbitux or cetuximab on advanced lung cancer. Next. So this challenge of going from free text to a structured format where we gather information from professional sources such as books, professionally authored sources such as clinical notes, and curated content either coming from professionals, maybe in WebMD, or generated by the community through Wikipedia or Health Forum, kind of shows you the spectrum of information that is available in free text format in the open world, right? The information space that we are working out of. Next. The challenge is to take that and convert it into structured data. And next, and the tasks that are needed to do that are to identify entities, to extract attributes from about these entities, to determine the relationships. For example, the fact that cetuximab is the same as Erbitux kind of says that you have cetuximab and Erbitux as entities, and advanced lung cancer is also an entity. Identifying relationship, the fact that cetuximab is used to treat advanced lung cancer is the relationship here, or the assertion. And then linking it to other resources, kind of saying really these two are the same because cetuximab is a synonym for Erbitux. Right. So this kind of shows you the kind of tasks that are needed to infer information in free text form and take it from the unstructured format, the free text format, to the structured format in a database or a table. Next. So one of the critical kind of tasks here, which will be focus of most of the talk today, is on named entity extraction. Named entity extraction is taking this document about Erbitux helping treat lung cancer and finding out the entities that are of interest. Next. It could be the relation itself, the assertion that Erbitux helps treat lung cancer. So that is an assertion coming from this document. Or it could be characteristics of that assertion, that the author in this case is Charlene Lino, or next, that it was written on September 23rd, 2009. Note that it doesn't say September, but it says sept in the document. So there is some sort of a normalization happening here, kind of saying sept in this context actually means September. And then next, it is coming from Berlin, and hence now you can open it up to other resources, kind of saying, okay, if it is coming from Berlin, then it is based out of Germany, or has European research maybe influencing this particular document, right? But named entity extraction is a domain-dependent task. What I mean by that is, depending on which domain these models need to be developed, it becomes critical to understand the characteristics of those domains. For example, next, in legal, you have the firm names such as Kirkland and Ellis, LLP, or the Skadden, Arps, Slate, Meager, and Flom, LLP. If you notice, the names are of the law firm, so these are organizations, but they are formed out of names of partners within the firm. So traditional named entity recognition model that identifies person names would identify the name Kirkland or the name Ellis or the name Skadden and so on. But linking it together to kind of say that this is not really talking about a particular partner within the firm, but the firm itself, is a task that is defined and relevant in the context of the legal domain. So when I say domain, I'm kind of talking about a field of application of these named entity models. Another example is from finance. In finance, especially just looking at stocks, you would know that the symbol QAN.AX is the ticker symbol. So that has meaning only in that field. And then it maps to Qantas Airlines Limited. So that would be the name of the organization. And then you have the value 2.11 with or without a currency symbol. That is basically a currency value, right? A monetary value. So in finance, the concepts such as ticker symbol, which is all capitals but has a some sort of a context and a framework of where which symbols are relevant and which are not, is going to be important. And then you have organization names, and these organization names are going to be different from the organization names in the legal field, which we just saw about. Next. In medicine, we have a much wider scope of entities present. So one category of those would be protected health information, PHI, that are defined by the HIPAA Act, the Health Information Portability Act. So for example, names, dates, addresses, zip codes, geocodes like latitude and longitude, phone numbers, fax numbers, email addresses, social security numbers are all personal identifiable information. And so are medical record numbers and doctors' names and the hospital name and the date of visit, age of the patient, if it is greater than 89, for example. And any other features, including facial images. So the visual representations, the photographs are all also personally identifiable information. Next. A slightly different for domain would be in the pharmacy domain, which still, if you say, is broadly defined within the health domain, right, within the medicine domain. But the concepts are very different. They are not really focused so much on personally identifiable information or protected health information, but really on the drug and the dosage and so on. So in this particular example, 2 puffs orally Q4 HRS X90 DYSVs is Latin and Greek, so to say. For us, it may not necessarily be understandable unless, next, if you kind of understand that dosage in this case is 2. And this is about a medication direction. And so 2 puffs taken orally every 4 hours. So Q4 HRS is the frequency that kind of indicates that it needs to be taken every 4 hours. X 90 days is for 90 days, and V's is the reason for why you are taking this. So this is a Ventolin aerosol puff that is getting prescribed, kind of saying you need to take 2 puffs orally every 4 hours for wheezing. So uh, as you can see, these two, even though they're coming from the same or related domains, they have very different kinds of concepts. The previous slide was really talking about 2 different domains having the same concept of organization, but having different features that define those organizations. Here, we're kind of talking about the same or related domain that have concepts that are widely varying. So this is the landscape of named entity extraction. To the extent that people in clinical domain argue whether they should be called named entities or they should just be called clinical entities, right? They are not necessarily named entities because the same features don't apply here. Next. So overall, what this is kind of showing us is that there is need for annotated data sets that are domain dependent data sets that can highlight the problems that we want to study. So next, looking at the approaches that can be used. So in this case, annotated data sets are critical for training a model. So that's the supervised learning framework to kind of understand what are the classes of interest. Next. Defining these classes of, even if it is from the medical field, are we really interested in concepts that identify protected health information, or are we interested in these medication concepts that can be derived from directions that go into a pill bottle, right? Uh, but nevertheless, it is a very effort intensive and costly uh, endeavor to collect these annotated data sets. And the question always is, next, how much is enough? How much data is enough? Should we create a data set that is representative, which means that we take everything that happens in a day, because any day chosen at random is representative of how of data, and then kind of just annotate it? Or are we selecting it based on the classes of interest or the task that is at hand? Next. So this brings us to this notion of rare classes. Yes, there is need for annotated data set. Yes, it needs to be representative, but how do we define that representativeness? Specifically, if you look at medication entities coming from clinical notes, and we have a relatively large set that has about 84,000 medication entities identified from these different classes. So for example, the drug name, strength, form, dosage, duration, route, frequency, reason for giving this prescription, and any adverse effect that might be caused because of this drug is a great task setup for pharmacy for medication extraction, right? Next, but if you look at this data set, which is 84,000 medical entities, you'd see that the distribution is not uniform across all of these classes. Almost all notes have almost all medication kind of documents, let's say prescriptions will have drug. So that is the most frequent class. But then strength, form, frequency, route, dosage, reason are not necessarily um, available for every direction. And even more problematic is the number of times an adverse drug event or duration is annotated in the data set. So this graph is kind of showing that among the 84,000 medication entities, really only about 1%, actually even less than that, were duration class entities. About 2% were adverse drug event class entities. And I could put dosage and reason also in relatively rare, in the sense that they are only about 8%, which is about 5,000 entities over this entire data set that are related to reason and dosage. So that is one problem. The problem is the relative frequency of a particular concept might be low. Next. Another example would be in a similar task, but coming from social media. Again, similar task as in named entity recognition task coming from social media, where um, the um, so I have a question in the question answer phone which is relevant here, so I'll take it right now. So why are the 68% of knots missing in drug name? It's actually if you go back in one slide, please, thank you. It is so this graph is normalized across all classes. So 68% is not really if you add up the rest of them, that's 68%. So what this graph is kind of showing is 32% of the 84,000 medication entities are drug entities. If you look at the number of documents, every document, so 100% of the documents that we had actually had drug mentioned in it. Okay, so we are not showing the relative frequency in terms of how many documents have the concept, but really how many of your annotations are coming in a particular class. Next slide, Shinian. Thank you for the question, though. And that had helped me clarify the graph. And we'll see the same graph 4 times. So perfectly timed question. Thank you. So this slide is kind of showing how the rare classes would be in tweets, where the tweets are annotated for names of people, products, whether they are creative products, location, group information, corporation, and so on. So here, note that only 1,000 tweets were annotated. So even though 14% of them are on product, really we are talking about roughly 14 like 140 examples of them, and that is still so there's a number that is an issue as well. So if you have very few, like 40 annotations for corporations, that's going to be very difficult to train a neural network model or some deep data science model. Next. And then there are questions that could be asked, similar questions that could be asked for a classification task. So in this particular case, we have tweets that were annotated as those that had an adverse event related to a drug and those that did not have an adverse event related to a drug. So that's what an ADE stands for, adverse drug event or adverse drug effect. So it needs to be an adverse effect related to a drug, which is also mentioned in the tweet. So I bring up this example because this is a much larger annotated data set. 25,000 tweets were annotated. But as we would expect, people don't really necessarily tweet about drugs and adverse events and so on. So even if we do selective sampling and kind of create a data set that is really talking about drugs and adverse events, only 9% of these, so just about 2,500 tweets overall, had any mention of adverse event, and there were about 22,000 tweets in that data set that did not were not about adverse events, even though they had mentions of drug names in them. So what does this tell you? This tells you that this has both problems, right? It has a problem in terms of number of instances in the positive class. So ADE will be our positive class, so that we can train the models. But also the skew of distribution makes it really hard for big data approaches to try to identify needles in a haystack, right? Identify these rare classes or the rare entities within this large kind of fire hose of data that comes our way. Next slide. So now kind of Shinyan would talk about 3 specific data sets that we would be using in our talk. So this kind of talks about the specific data sets that we would show our experimental results on. Shinyan.
All right. Thank you, Vinod. So hi, everyone. I'm Shin Yan. So basically, many entity extraction data sets are out there. So here we mainly introduce 3 of them. So each of them comes from a different domain, and each of them will present a unique type of challenge to this data to this task. Right. So the first one is Conditional 2003, so which is a very standard data set that has been widely studied across the years. I think many of you might already know this data set. So it has 4 classes, namely person, location, organization, and miscellaneous. For example, he was born in Berlin in 1918 and married Elena Bell. So here Berlin is the location name and Elena Bell is the person name, right? And another example, he entered the military college in 1935. Here, the military college is the organization entity here. Okay. So the second data set is called UNA 2017. This data set is particularly focusing on the emerging entity extraction. By emerging here, I mean all the data set that we see that we see in the in the data set in the development set or the test set will be unique compared to the training data. It will never show up. You will never see any of them in your training data set. Okay, so it is collected from social media over Twitter, and it has also 1,000 tweets, and it has 6 classes: person, location, corporation, product, creative work, and group. Right. For example, Amazon UK offering HTC Desire Z Unlocked. Here, the Amazon UK will be a company name, so we'll classify it as a corporation. And HTC Desire Z is a particular version for a phone, I think. And so that's why we call it product here as labeled. Another example is that anyone going to see the Friday Night Lights. Here, the Friday Night Lights is a movie, so we're gonna we label it as a creative work. Okay. The third data set is called N2C2. So that it actually comes from a national NLP clinical challenge in 2018. So it focuses on extracting medication-related information from clinical notes, as Vinod has described earlier. So the medication information here includes 9 different types of classes: drug, strength, form, dosage, duration, route, frequency, reason, and of course, ADE stands for adverse drug events. Okay, for example, this is one example that we've just saw earlier. The 2 puffs already Q4 hours times X 90 days for weeks. So here 2 is the dosage, puff is the form of the medication, and orally is the route. Indicating how to take the medication, and Q4 hours actually means every 4 hours a day. No, it's not a day, it just means for every 4 hours. And X 90 days is the duration, like how long the patient should be taking this medication. And weeks here is the reason for this medication. Okay. And for another example, patient developed rash around arms after starting antibiotics. So here, the text span rash around arms is a complete entity, ADE entity that is associated with this antibiotics. Okay. So now I'm going to hand it back over to Vinod.
Thank you. Next. Okay, so this kind of is now we are kind of defined our entity classes, defined what we are calling rare entities, and the different characteristics of the rare entities. And now let's go into the next phase, which is the identifying rare attributes. In this task and in this kind of section of the talk, we are going um, to to look at identifying rare attributes from clinical narratives, and through this example look at a typical natural language processing pipeline that is created, and introduce kind of approaches that are used and are still useful for identifying attributes, especially if there are when we have very little training data for those. So the goal here is to use medical records to identify patients who meet the selection criteria for clinical trials. Okay, so the task here next is the setup is that a patient can either meet a criteria for selecting for a clinical trial, does not meet the criteria, or possibly meets the criteria, so they need to be evaluated nevertheless. Right. The criteria that were used partially because they're coming from real life clinical trials, but they were also selected criteria so that their data set could be created, and some sort of a benchmarking could happen across multiple systems. So the attributes that are of interest for this particular task would be substance abuse, which means identifying patients or members from the cohort, from the data set, that have a prior history of drug abuse and alcohol abuse. Next, um, looking at specific numeric inference based on values that are available from clinical narratives. So for example, what would be a person's creatinine level or hemoglobin A1C level? For those who are not well conversant with medical domain, the hemoglobin A1C level would indicate whether you are diabetic, pre-diabetic or not. So if the value is 6 or low, I believe it is considered normal. If it is between 6 and 6.5, it is considered pre-diabetic. If it is greater than 6.5, it is considered diabetic. Next, you could have complications, and these complications could be either they have had myocardial infarction, which is basically heart attack earlier, advanced coronary artery disease, or major diabetes related complications, ketoacidosis, which is also a diabetic related complication, but something specifically pointed out, and whether they have had abdominal surgeries or not. The reason why I'm kind of showing these examples here is to show to you what are the different kinds of things you could pull out from clinical narratives, right? Where the definition of those classes are not necessarily complete set. It is clear what HbA1c level is. It's one value, right? But it's not clear what an abdominal surgery would be, and what even though there's a rough idea and understanding of what abdominal surgery is, whether surgeries that are done near the abdomen but not in the abdomen, are they considered abdominal? Would be the question that needs to be kind of answered and defined here. Next. Medication history, where it was something about whether they take a particular drug for a myocardial infarction as a preventative, or whether they take some dietary supplements or not. Again, this is a open-ended kind of list, because we don't really know what a dietary supplement is. There's no kind of hard and fast definition of that. Next, uh, there were also of two criteria that were about whether they were able to make their own decisions. So either they are cognitively able to make decisions, or whether linguistically, whether they are proficient in English, and so they can communicate the decisions once they make them. Next, the challenge and the reason why I want to kind of highlight this in this talk is because of the skewness of the distribution in the training data for these sets. So these are the same, all 13 of those categories. About 200 notes were annotated with these labels, and so all rows here would add up to 202. Okay, but then you'll see that alcohol abuse, for example, was present only in 7 of the 202. It was not there in 195 of them. Another rare class would be the drug abuse class. So both substance abuse classes were rare in this set. Yes, Paula, it is published research, and I'll point to that paper at the end. The so whether they were proficient in English or not was also rare, because it was rare on the non-English side. So it was so predominant that 192 out of 202 are proficient in English, which means the problem becomes the inverse problem now. How do you identify people who are not proficient in English, right? So the not met class is the rare class, and the one that takes the cherry that takes the cake is really ketoacidosis, where no examples in the training data were examples of met, which is a problem because you don't have any examples, but you know that you need to identify patients who may or may not have ketoacidosis. Next, as you can see, 6 of the 13 criteria here are what we would consider rare classes. So how do you go about doing it? If you go only by numbers, maybe all of them are rare, because you're really talking about at most about 70 to 120 um, uh, examples in the positive class or the negative class, right? So that is still not too much numbers, but that still is something that was the characteristic of this data set. Next. So what do you do when the classes are rare? Especially for examples like drug abuse or alcohol abuse and so on. Next. So the approach that we took was really to analyze every met and not met case in the training data, really try to learn from each example and to kind of see whether we can generalize from them. So next, looking at starting from the smaller class, and then looking at what are the patterns, or what are the kinds of variations that make that into that you can learn from, so that you can generalize from those. Remember, the whole purpose of supervised machine learning is to generalize from the training data. So it is, if you are able to do well only on the training data and not any other example, you have not really learned much. You have just memorized the training data, right? So the challenge is to learn to generalize. And now the question is, what are the generalizations that can be done? For example, what are the linguistic patterns that you can derive based on the examples that you know for sure are from these rare classes? Next. The challenge of ketoacidosis was worse, as I said, but uh, note that that concept is not unknown to the medical domain, right? So ketoacidosis is a known condition, and so understanding that domain information and trying to kind of transfer it over to this task becomes a challenge that happens here. So how can you deduce possible cases of MET? So in a way, we are justifying why 202 out of 202 are not ketoacidosis. If you're able to justify each one of them, you have learned your model to kind of say, if it doesn't meet these criteria, then probably it is a positive case of ketoacidosis. Next. Um, so this is kind of the building blocks of creating this NLP pipeline. Usually the natural language processing kind of step always is a pipeline. I'm not saying that it has to build on the previous one. You could do a joint learning kind of a model, but it is still has a series of steps. So for example, you need to pre-process your data. So you need to split the documents into sentences. You need to tokenize a sentence into words or tokens. And then you need to do some specific pre-processing that is relevant really only for the domain. So for example, if it's Kirkland and Ellis LLP, you don't really want to split it into three different entities, Kirkland, Ellis, LLP, right? Because then it will be person name, organization, which is not the correct labeling. The Kirkland and Ellis LLP is really one organization. Similarly, in the health domain, there is some sort of a rough structure to the notes. There are sections. So there is a section for personal history or social history. There is a section for family history, for assessments and plan, for diagnosis, and so on. So they are for medications that are prescribed. So all of these kind of sections within the notes. So identifying them could help identify whether somebody has had a past occurrence of myocardial infarction, or whether their parent had the myocardial infarction and it's not them, right? So whether the information is coming from family history or social history would be relevant in this case. Next. You need to split records by date for temporal analysis. So if you noticed, some of them were ketoacidosis in the last year, or myocardial infarction in the last 6 months. So you need to kind of do some sort of temporal inference of really when the last occurrence of heart attack happened, right? Next. And then once you have done these pre-processing, then you're doing the content analysis, and that's going to be the next few slides. Next. So one way to learn information about the rare classes is to identify templated elements from free text. So yes, sections help, but then if you click again, there are some that are in a way templated in how it is written. Dates, phone numbers, email addresses, URLs there is a rough format, and they follow a particular style, right? And so if you're able to identify that through regular expressions, next, then you are able to build on top of that. The next kind of example would be if the information is available from a key value pair. So something colon value. Okay, so that will be a key value pair. So in this case, it is HbA1c colon 6.7%. It's kind of telling you that 6.7 is the value for the key that is HbA1c. That tells you that 6.7 is the value for HbA1c. But then you might have other information also in that line or nearby, which kind of says normal colon below 6, pre-diabetic 6 to 6.5, diabetic above 6.5. This is basically the information that I gave you a few slides back. But this is kind of saying some context to what the 6.7% is. So inferring from 6.7% to call it diabetic needs next level of processing, where you're kind of saying, okay, if the value is correctly identified and then the value follows a particular range, falls in a particular range, then you are going to characterize it as diabetic or pre-diabetic, right? So that would be the next level of kind of information synthesis that needs to happen. Next, but this information can also come from tables, and then you need to kind of understand what information needs to be pulled from external sources that are relevant to this task. Next, so specifically, uh, every class, in addition to knowing for kind of describing the definition of the class, it is also important to know what is the knowledge that can be gathered from external sources. Next, an example of that would be alcohol abuse and drug abuse, where if you see, there are lists of the substances that people abuse, right? Alcohol, methamphetamine, so that's meth, ecstasy, or marijuana if it is not medical marijuana, and so on. Right, so there are lists of substances that need to be kind of included, and sometimes it would not show up as alcohol in the clinical notes. It could show up as these many kind of drinks, this many number of drinks, or this much wine, or this much vodka, and so on, right? So then so it will be like 2 shots of vodka or something like that, where again you are using units that are relevant for the particular substance that was abused. Next. You could have modifiers or related words like binge drinking or addiction or abuse, which are stronger words to indicate a definite abuse rather than words that are just like social drinker, which would be a milder definition of alcohol use. So it will not be an abuse. Next. And then there are some that are associated complications related to alcohol abuse or drug abuse. Example would be inebriety or insobriety and so on, or sometimes kind of agitation, things like that that might actually associate with heavy drinking. Next. Another example that I kind of alluded to earlier was when you have, in this case, abdominal surgeries, you don't know the list of surgeries beforehand, but you can always go and look up the different kind of surgeries that are performed in and around abdomen and include that as a list. So now suddenly the knowledge acquisition is not get a list from the web and put it in, but really seeking out exactly what is a relevant list, and is web the right source for it, right? So the next slide. So where would those sources come from? So one of the first examples next is domain dictionaries. So what I mean by domain dictionaries is when you have a particular field of interest, you would have a list of terms or list of entities relevant in that domain. So for example, there will be gazettes where you can have names of all countries or all states, or names of all law firms or all organizations, names of all ticker symbols, right? So even though your data set has only 15 instances of ticker symbol, you know the span of ticker symbols is really based out of those that are registered in a stock exchange, right? So there is a possibility of getting it from there. Similarly, in the medical domain, you could get ontologies of these medical concepts coming from UMLS Meta Thesaurus. UMLS stands for Unified Medical Language System. Or specific dictionaries that are used by certain health professionals. So RX norm is a pharmacy specific dictionary, but that's also included in UMLS, by the way. But it is really about prescriptions and the packaging it comes in and so on. Next. Um, I should not kind of diminish the importance of human experts here. So even for this task and the follow-up task that we have worked on, and Paul asked about published paper about it, we have reached out and collaborated with experts at Michigan Medicine who have helped us expand these lists and make these systems more robust, and or identify what constitutes an abdominal surgery and what is not, right? So that kind of helps immensely. And so I would not belittle the importance that human expertise actually gives in this case. And so the challenge then would be, how do you capture the human expertise and how do you put it into the model? Next. So once we have these kind of knowledge sources identified, the approaches that we use is kind of a hybrid bag of approaches. There's contextual data analysis, where you are learning from the examples and seeing what these examples tell us about the task and about the domain. What are the linguistic patterns that can be used, and what are the how do you kind of use keywords to identify which sections are relevant in a clinical note, or which term is indicative of a concept. So for example, if LLP comes in and you have a list of last names before it, that as a whole will be a name of a law firm, right? Just so you know, there are some electrical outages here where I'm in my office, so that's why you're seeing me go in and out, as I'm hoping that that's not too distracted. Okay, so finally, once we have done what we can using these knowledge resources and patterns, it is the other arm of identifying named entities, which is really a focus of a lot of data science research, is identifying named entities using supervised approaches, right? Use of domain knowledge into the model. How do you integrate this? How do you learn models that are traditional machine learning models, which are support vector machines or conditional random fields now, and more and more into deep neural network models. And that is a section that I want to kind of leave for the third part of the talk. Next slide. So this kind of ends the second part, but I want to leave with evaluation. And so in this task of evaluating rare attributes, if you click next, Shinyan, this model that I kind of presented uh, gave the best published performance on this N2C2 2018 task on cohort identification. Our micro averaged F1 on the test set was 0.911. Just so you know what macro averaged F1 is, F1 is a harmonic mean of precision, which is positive predictive value, and recall, which is sensitivity. So it is a measure that is formed by for in the medical domain, you know these by as a positive predictive value and sensitivity, and for those in data science, you know it as precision and recall. Higher numbers are better, one is ideal. Our micro averaged AUC, that's area under the ROC curve, was 0.9103 as well. And this paper, coming back, Paula, to your question, was published in JAMIA, which is a journal for American Medical Informatics Association, in 2019. And I can send you the pointer to the paper later on. Okay, good. This is a good time for a break and a question session. So if there are any questions that you have, this would be the time to kind of raise those, and I'll give you a few minutes for you to formulate your questions before we move on to part 3. Shineen, you could go to the next slide.
Yeah.
Thank you. Okay, hearing none. Let's move on, and as I promised, we would have enough time after around 4 or soon after 4 to take additional questions. So please keep your questions coming in. Okay, next.
All right, thank you, Vinod. So starting now, I'm going to introduce some of the approaches that used by people for named entity extractions and the approaches that we developed in our group. So over the years, we have observed the fact that the approaches for entity extraction have traveled from rule-based methods to machine learning-based methods. And now, since the deep learning methods are with the neural nets have shown promising performance across different sorts of tasks, so it has become dominant in this task as well. So with the rule-based methods, we need to manually define a set of rules that are associated with the entities. Right? For example, here on the right, he lives in LA, and here LA is the location entity that we would like to identify. So if we can observe lives in a text, so that will be a rule that can indicate the successing words or the token will be a location name. Okay. So in traditional machine learning models, we have to manually define a set of features and then feed it to the model. So, and then the model will try to automatically learn towards a particular training objective. So here I'm going to give a very simple example using what's called conditional random fields, or you can call it as CRF, which is a very popular and powerful model that developed for recognizing entities from text. Okay, so essentially what it does is that it will try to, after we have a data, so in here, Michael Jordan was born in Brooklyn, and then we need to identify, we need to develop a set of feature sets for each of the token, and then we feed the feature set to the model, And then what the model essentially does is that it will try to automatically learn from the feature set so that the likelihood of the target label sequence will be, given the current input, will be maximized. Okay, so this is what the model is trying to do, so that then we can find the best sequence of labels that can maximize the likelihood of which can be maximized. Okay. And now with more in these years, and more people have been trying to use neural networks to do this task. And so with neural net, the handcrafted features is replaced with with distributed word representation, which we also would like to call it as embedding. So here I'm showing one of the most popular framework that used for entity extraction. We call it RNN-CRF or LSTM-CRF. It depends on what type of recurrent neural net that you want to use here. Okay. So essentially, given our input data, Michael Jordan was born in Brooklyn, and then we will acquire the word embeddings from using a pre-trained word embedding system, so that we can have a representation for each of the token. And then essentially the recurrent net LSTM here will take as input the word embedding of each token, and as the output, we will have a vector-based hidden state for each of the token. And because we can read the text from both forward and backward, so that the LSTM here is bidirectional, so that it can model the text from both of the two directions. So therefore, after we use the LSTM to model the text, for each token, we will be having two hidden states, one from each of the two directions. Okay, and then for each of the token, we will combine the two hidden directions from hidden states from two directions, and then we send it over to the CRF layer that is on top of the LSTM, and to make a final decision. And please note that the CRF here is not the same as the CRF model that we introduced in these slides. Okay, so this is a what we would to differentiate them well. So we would call this CRF here as a traditional machine learning model. So that's a complete package. And in here on the CRF is a CRF layer. So it will essentially functions similarly as what the CRF model tries to do. Okay, so similarly, the CRF layer will also try to make the predictions over the given input sequence by maximizing the log likelihood of the sequence. Okay. Okay. So these methods can also be extended to a more general version. So where we would have a neural net that serves as an encoder that extracts hidden representations from the data. And on top of that, we can use either a CRF layer or any other output layer, such as a linear transformation, to make predictions. As of now, the current methods function by treating all the tokens equally, including both entity tokens and the background tokens. So we believe that the model would work better. So if it could be indicated by the presence of an entity in advance. Okay. So ideally, what we hope is that given an input sequence here, I'm using the same example, and there could be an indicator. So what the indicator does is that it will tell which tokens are more likely to be entity tokens. So such like this. So in this particular example, Michael Jordan is more likely to be a entity token, and ideally Brooklyn is more likely to be an entity token. Okay, and then if we have this information, and we can inform the following module, so that the output layer needs only to focus on these tokens. Okay. So here I'm going to show how the model works on a particular token Jordan here. So the words Michael and lives are context words on the left and the right? So first we will have embedding for each word like this. And then we will use a LSTM encoder to get the hidden representation for each word in the text. Okay. And we will have the hidden representation, and then here we just denote them as H. So HT is the current step representing the word Jordan, and HT -1 is corresponds to Michael, and HT +1 corresponds to lives. Okay, and then we will combine these hidden states with other states from, for Jordan, we'll combine its hidden states with other states from its context, and then use an entity indicator to decide whether or not if this word Jordan is an entity word. So the indicator will use an convolutional operation to combine the values in those hidden states. And as the output, the indicator will inform the following module how likely the hidden state of the current token, Jordan here, contains entity information. So we do this by scaling the hidden representation, hidden state of the word Jordan HT with the probability P here. So probability is the output of the entity indicator, indicating how likely the token is an entity token. Okay, and by scaling HT with P, we will have a new hidden states. We call it the GT here. So we just use GT as a new state for the token Jordan. Okay, and at the same time, we can acquire G prime T using the same methods, and except that the probability here is 1 minus P. Okay, so it will tell this one will tell the model how likely the current token is a background token. Okay, so these two are essentially the same operation, except that the probability are different. Okay, so the first one for GT, we use the probability P, and for G prime T, we use 1 minus P. Okay, and after we have these two states, G and G prime, for each of the tokens in a sequence, we can use a CRF layer to make predictions. Right, so we gather all the GTs from using the P on the left, and then we can also have, and then we can use a CRF to make predictions, and to make predictions of the label sequence. And also similarly, we can use G prime T, and with the same CRF, we can also have a predicted sequence of labels on the left. Okay. So this is the workflow of this model. We call it focused name entity recognition. Okay. So now the problem is how to train the model. So we have 3 training objectives for the model. So the first one is designed for the indicator. So we just treat the indicator is treated as a standard binary classifier where we just use the cross entropy function to do that. So on the left is the predicted value, and here we use the linear transformation to do that. And on the left is the binary token, the binary labels that we assigned for each of the token. So we just treat all the tokens that has an entity name as 1, and all the background tokens as 0 or as others. Okay. So for the mean predictor, it is trained by minimizing a negative log likelihood. So the target label sequence is the gold annotation here, which is what you'll see here, Y1 all the way to YN are the gold annotations that we have available in the training data set. And the G1 and G1 to GN is the other new hidden states that we required using the probability P. Okay, and for this, so for this auxiliary predictor, where we use G prime, we also minimize the we also similarly minimize the negative likelihood. The only difference is that the target label sequence here are all background tokens. Okay, so this is saying that we require the model to not only make correct predictions given the current information, given the current indication, but also that when we use 1 minus the indication to indicate the model, we hope that the model would be the output of the model is supposed to be all background tokens. Okay. We evaluate the model on 3 data sets that we introduced earlier.
Shinian, would you be willing to take a question on the model? Sure. Naihao Deng has a question, but Naihao, would it be possible for you to write it down in the question and group in the Q&A window, please? I see that you have raised your hand, but I don't see a question. Meanwhile, there was a question in the chat window that I still wanted to kind of bring it to your attention so that you can answer it as well about, and it will be helpful for the rest of the attendees as also. Why wouldn't we find a representation of Michael Jordan as a whole and look at them as separate words?
Oh, that's actually a pretty good question. So I think that has something to do on the embedding layer. So it depends on how do we initialize a word representation for each of the words. Well, I think, yeah, I think that's a very good idea to try that. But in our case, we just in our experiments, we just stayed with the standard way where we acquire a word embedding for each of the tokens separately. So we believe that when the intuition behind this is that we believe that when we use a pre-trained word embedding that is trained over a large corpus, we hope that using word embeddings separately for each of the tokens should be good enough. But I think your idea is worth of trying.
And it's worth noting that the definition, the representation for Jordan would be assisted by the representation for Michael and Lives, and these are kind of word representations that get kind of appended together for the contextual nature of it. The other reason also is that the I was going to say something and I forgot. Oh yeah, so Michael itself, you don't know that it is an entity yet, right? And so in the training, yes, you can train it that way, but in the test phase, you kind of you don't know the label for Michael or to Jordan. The task itself is to identify Michael Jordan as an entity, so you don't know that during inference stage. Okay, so Naihao's question was that he was concerned about the difference between the main predictor and the auxiliary predictor, and checked whether wanted to check whether we used BERT embedding here.
Oh, so we so in this particular model, we did not use BERT yet. So we just we use the standard LSTM as bidirectional LSTM as our main encoder. And what do you see here? So what do you see the two CRF here? So the CRF layer are shared by these two indicators, meaning that they are using the same setup, just that the inputs are different. The first input in the left part, in the main predictor, the input are all the G states, and on the right, the inputs are G prime states.
Other question from Junji is it true that for each word in the training network, there is a label corresponding to each word?
Yes. So in the training data set, so basically named entity extraction task is you can generalize it into a classification task on token level, meaning that each token in the data set will be assigned with a label. And the label is usually predefined.
Yep, thank you. That's the questions for now.
Yeah. Okay, so now we can go to the evaluation page. So we evaluate our model on 3 data sets that we have introduced earlier. So on Kano data set, so for the classes that we have improvements over, the model usually favor, we observe that the model favors the precision. We explain this by the fact that when the indicators can perform good actually on Conditional data sets, the indicator can perform very well. So it's more than 95, 0.95 on the F1 scale. So the model, when we have a good indication, the model can have a better judgment between entities, not entities versus background words, but entities of one class versus other classes. Okay, so therefore it results in better precision. And after the error analysis, we found that as you can see here, the performance on the miscellaneous label continues to be lower. So the primary issue with this particular class is that we don't have a very clear definition for this class. For example, in a training data set, if you for the word European, it will be classified as miscellaneous. If you have, we also have things like pro-European, which is also miscellaneous, and the Princess of Luning is also miscellaneous. But because we observe the princess of something, the model can be easily tricked into classifying it as a person. And because of the understanding of the pro-European here, sometimes the model will misclassify it into other classes as well. Okay. For the UNAT 17 dataset, we can see that most of the improvements that we have comes from a better recall. So this is because that the indicator itself on this dataset do not work very well. As Vinod introduced earlier, that on this dataset we only have a very short number of instances for each of the class in the dataset, and in total we only have to be fair, in total in the training dataset we only have like 1,000 tweets. Okay, so the indicator does not work well, so it does not have a very good job on identifying entity tokens. Okay, so basically, even if we do have improvements over each of the classes, most of the classes here, and especially the recall over every classes here, the performance on all classes are still lower, okay, than expected. And the primary issue is that this dataset is designed for extracting emerging entities. So it means that all the instances that we have in development set or test set has none of the have zero overlap to the original training data. Okay, so that's the key challenge of this dataset. On N2C2 dataset, so for the rare classes like duration, reason, and ADE, we improve the performance by mainly having a better precision. So this is essentially because the indicator can reasonably identify the entity tokens. Okay, and that's why we can observe a better performance here. And again, because as earlier said, the number of instances that we have for the three classes, duration, reason, ADE, are very low. So that's why, well, even if the overall, even if we have a better performance here, the overall, for example, for ADE, we actually have a improvement by more than 5% here. But on the overall performance, we can see that the overall improvement is still in a small range. And this is saying, I think this is passing one of the message that we want to tell everyone here, and is that when we look at the overall in named entity extraction task here, when we usually look at the overall performance, but if we to really make sure that your model is really working, we have to make sure that the model should be also working very well on the rare classes like this one. So in this case, we do have an improvement over these rare classes, but we still think that there's a lot of work to be done to further improve this model so that the work can, the model can really work very well in a real world data set. After the error analysis, we can say that we want to say that the performance on the duration ADE, the reason is still need to be improved. And the primary issue is one is that there's are a lot of out of vocabulary terms in a data set. So for example, here, what you'll say here, the duracest and tachycardiac are all missing from our pre-trained word embedding. And also there's another key challenge in this part is that it kind of there are some of instances, the identifying of which really requires a domain knowledge, because even with the same word in medical domain, it can refer to different concepts. Okay, so for the following two examples, Shisang furosemide and became hypotensive here. The hypotensive here is the ADE. But if we add another phrase right after this, saying that she became hypotensive requiring norepinephrine. So in this case, the classification for hypotensive should be reason, because the hypotensive, the medication here, norepinephrine, is really the reason for this hypotensive occurrence. Okay, so that's why this data set is considered very challenging compared to a regular named entity extraction task. So in the next step, we would like to try using in-domain word representations. And also we want to customize our FONER into a version where we can focus on a classes of interest instead of all the entity classes at the same time. And also we are planning on to try to incorporate domain knowledge into this framework so that it can perform better on the classes. Okay. So earlier, Vinod also introduced a rare class issue of the mention of drug adverse events on Twitter. So here I would like to briefly showcase one of the previous work in our lab on this task. So I will focus on the strategy of using the collocation information here in the data, and the collocation embedding. The collocation embedding here is created for tokens that are medically meaningful. So we use, basically for each of such tokens, the tokens that have a medical meaning, and we collect its neighbors from dataset. And then we use the embeddings of those neighbors to form a collocation embedding. Okay, so we found that using this very simple strategy compared to a standard attention-based LSTM model, our model, we call it as CLAPA here, can achieve a better performance due to a better recall. So all the other stuff here, as you can see, the other embeddings, you can use it. You can use any other embeddings as you wish. So in our case, the other embeddings here is a standard pre-trained word embedding on Twitter. And the collocation embedding is what we created using the collocation information for the medically meaningful words. And the encoder here is a attention-based encoder using LSTM model. So the task here is for the model to decide whether or not a tweet that has a mention of a drug name is talking about a ADE or not. Okay. We evaluated our model on this data set. So this is the share task on social media mining for health 2019. And we evaluated our model on this data set and using two baselines. The first baseline is a standard SVM, and the second baseline is a attention-based LSTM model. So we can see that when we building on top of this attention-based LSTM model using collocation embedding, we can significantly improve the recall here, and therefore to result in a better performance. Okay. So now I think I'm going to hand it back over to Vinod. Is
Yeah.
there any
Yeah.
questions?
No, but I just want to kind of leave the final slide on and then can open up for discussion. But if you go back to the previous slide, a minute, no, the next one, sorry, 63. Thank you.
Okay.
Sorry, 63.
Okay.
Yes, the point I wanted to kind of include here is just that if you recall, this data set was the one where we had 9% ADE and 91% non-ADE. So the baseline model is will have an F1 if you say everything is as yes, which is because only 10% data is ADE. This would be around 18%, like 0.18 as F1. So the even though the F1 here is kind of showing up as 0.568, which appears low, for the skewed distribution, the random baseline would actually be pretty low at about with F1 of 0.18 or so. So that was the point. That doesn't mean that the problem is solved. It is far from it. But I wanted to give you some context in interpreting F1 values here. Okay, next. So I want to kind of leave this slide up, kind of to summarize this talk and this mini workshop. So next, so it is that named entity extraction is an important task within the natural language understanding, kind of for natural language understanding. But different domains need different things. So their definitions are different. The complexity of the entities are different. So um, the rare classes within these domains present a unique opportunity to kind of incorporate domain knowledge, and this could come in different ways, using using some sort of kind of learning from external data, where you could have pre-trained embedding or knowledge resources, or other kind of patterns that you would infer from training data, or the next one is on deep learning and deep neural network models that provide a framework to incorporate this in a more systematic way. I'll leave this slide on as kind of one slide takeaway for all of you who have stuck with us to kind of to learn about these data science approaches and natural language approaches for rare classes. And I'll open it up for questions. We have about 5 more minutes, and I think I have answered all the questions that we got along the way. Nihao, you have another question, which is an open-ended question probably, and that is that did you test the model's ability for domain adaptation, like training it on a certain domain and a shot in other data sets, and does the model achieve decent performance in that case? Answer is yes. And Shinian, go ahead.
Yes, so we try to use our model. So there's a one particular experiments that we experimented. One thing is that we tried, which is we try to use FONER that is trained on the N2C2 data set and try to identify trying to identify medication information from clinical notes. And then we adapted the model using transfer learning to extract the same set of information, but not from the clinical notes, not from clinical notes, but from a pharmacy directions that are real world pharmacy directions, pharmacy prescription, sorry. So we actually ended up with a very high performance. And the key challenge there was because clinical notes were usually written by doctors, right? So when they try to when they talk while they are talking through with the patients, they will write down and keep whatever that they write down into the clinical notes. But the difference is that, and so that we can have a very long clinical narratives for each of the data instances on the node level. But for in real world, in the real world of the prescription, pharmacy prescription, what we usually have is that a really short length of a sentence. What we really usually have is a sentence of the really short length, right? So the short length will be what we described earlier, 2 pulse, 4Q hours and times 90 days and weeks. So something like that. So that will be the prescriptions that we have in our real world. And because of the fact that the data is written by different hands, and they have a different pattern of writing through those words. So if we directly apply the trained FONER model to this new data set, we will have a very severe issue of mismatching a lot of things. So for example, the mismatching really happens of the span. It's not the fact that the model cannot detect those entities. The model can actually, but it just the model will also will also introduce a lot of different noise. For example, the meaningless words, the stop words will be also identified as one of those medication entities. So to do that, what we do is that we actually try to find the common features. We call our model as lex transfer. So we propose a we proposed a attention mechanism based on lexical features, common lexical features between our source and the target data. And so that the model can, when the model makes decision, the model will be on the new data set, the model will be focusing on the common features that are shared by the source and the target domain. So that this, and in, if I may, so in our final evaluation on the new data set, our F1 score, on the overall F1 score on the new data set, we manually evaluated over like 300 or 500 instances, and our overall F1 was more than 95%. Vinod, do you have any add-on?
No, thank you for the question. No, I am really appreciative of the question, and that kind of helps us understand that absolutely there is there is a possibility of transferring it from one domain to the other. But note that these two domains were very aligned. So they are both medically related. One is medicine, one is pharmacy. But and so that is. That was possible to do it that way for all of these classes. We are trying to do those experiments when the overlap between classes is not as well defined, but that becomes more and more challenging as the difference between the domains increases, which is basically how all domain transfer tasks are. So it's not a surprising thing. It's just that it did work for medicine to pharmacy. Great. Gregory Wolf has a question. Curious if there are any viable alternatives to neural networks for this type of NLP. As we were kind of saying in the first half of the talk, that there are models that can work very well even without neural network models. So I don't think neural networks models are necessarily the first thing to try. It is data intensive, it is computationally intensive, and it is still pretty much a black box, which means that you don't really know why some things are doing this way. And especially for a clinical task, or for another task which is sensitive to errors, it is important to recognize what those errors are and being able to explain it. So so there is explainability issue that comes up as well. So one of the things that we're trying within the group is even if you're working with neural network models, to kind of try to incorporate explainability into the model. So can you identify examples that are from the data set that are stereotypical to explain away why the decision is the way it is. That said, there are other approaches like the traditional machine learning models, or even really nuts and bolts pattern-based models that should be tried. Sometimes they work and they give you state-of-the-art results. Thank you for the question. Nyhaus, next question is, are those experiments about the domain adaptation also included in the paper? The paper is not yet out. So for the domain adaptation one, it is under active review. But if you are interested, do reach out to either Shinyan or me, and we can share with you the paper once it is published or accepted for publication. Thank you for the question. That's right, Shinyan?
Yeah.
Yep. Um, we are at 4:15 or just a minute past. So I wanted to take this opportunity to thank you all for attending this workshop. I know in an ideal setup, you'd all be in a room and I could see your faces and we could clap each other. But we had, I think we did have a very productive discussion, and I really thank you for your engagement in this workshop. Thank you and stay safe.
Thank you.
Okay, I think we have just want to leave it on in case there are any attendees who had questions, but feel free to sign off. Thank you.